both are absent, I think so. So anybody else can start explaining adsorption and partition theories. Mohammad Rafiq. Rafiq, are you there? Yeah, explain about adsorption and partition theories, what we have discussed in the last class. Your voice is breaking. Say clearly.
Absorption P. Q absorption density divided by concentration of solute in stationary phase.
Okay, that is linear
Commonly,
absorption. Proceed next.
then,
Say about remaining theories.
absorption P. Concentration of absorbate divided by concentration of solute in mobile phase. Let's see. Is a equilibrium constant divided by absorption constant.
What? Equilibrium constant divided by adsorption constant. Huh? Both are same. K either can be called as equilibrium constant or adsorption constant. It's not a different term. Okay.
Yes.
Okay. Name the partition theories, what we have discussed.
Columnar efficiency. Partition coefficient, addition time, and broadening theories.
Okay, pa, thank you. Anybody else? Jackson. Jackson, say about adsorption and partition theories. Say fast. Joy John.
Yes, ma'am.
Yeah, proceed with the adsorption and partition theories. Say about adsorption and partition theories, what we have discussed in the last class.
Partition theories, they are the column efficiency parameters.
What are the parameters we have discussed? Joy John and Jackson will be absent then. Anybody else? Monisha?
In partition theories, partition coefficient constant equilibrium constant is equals to molar concentration of analyte in stationary phase divided by molar concentration of analyte in mobile phase. Retention time, the time between sample ingestion and an analyte peak reaching a detector at the end of the column is retention time. Ideal time is 2 to 8 minutes. Retention volume means the volume of mobile phase required to elicit a particular solute from the column. Migration time taken for the mobile phase to pass through the column is migration time.
Okay. Okay, good. Thank you, Monisha and Rafiq.
Thank you, ma'am.
We'll start with the today's class, remaining parameters of partition theories. So we have seen history, principle, and theories of column chromatography. Under that, we are discussing about theories, adsorption and partition theories of column chromatography, where we have completed adsorption theories, linear, Freundlich, nonlinear, and bed theory. Now we are in partition theories, where we have completed partition coefficient, retention time, and retention volume. So these are all the adsorption theories. And the theory for gaseous molecules and column efficiency parameters for partition coefficient, retention time, and migration time we have discussed. Now let's move on to the fourth parameter, capacity factor or retention factor. It is called capacity or retention factor. It is denoted by the symbol K dash. Okay. It is called as retention or capacity factor. It is nothing but it is used to describe the migration rate of an analyte on a column. Migration rate of an analyte on a column. If you consider this is a column, we have seen migration time for mobile phase here. This is indicating mobile phase. Time taken for the mobile phase to pass through the column is called migration time, where this capacity factor is related to migration rate of analyte on a column. How much rate it is migrated onto the column. That is represented with capacity factor or retention factor. How long it stays in the column. Your analyte, how long it is staying in the column before eluting out, or to reach 50% elution retention time. This also a factor depends depending on retention time. So that means the retention time, your qualitative parameter depends on capacity factor. Here it describes migration rate of an analyte on a column. What is capacity factor? Migration rate of an analyte on a column. Migration here represents migration or adsorption, whatever principle it follows, the solute, how long it stays in the column, stationary phase. That represents migration factor or retention factor. The retention factor for analyte, a single analyte, to consider your analyte as A, then it can be defined as retention factor for A, that is equal to retention time, the difference between retention time and migration time, that is Tm and Tr, RT and MT, migration time and retention time divided by migration time, which will give you the factor, retention factor. And these two values are obtained from the chromatogram. You can see this is the chromatogram, where we can find migration time and retention time, from which the factor, retention factor, is calculated. It will say about how long your analyte is staying in the column. That is migration rate of an analyte in the column. When an analyte's retention factor is less than 1, this retention factor case, if it is less than 1, then elution is so fast. That means your molecule will be staying in the stationary phase for less time. So the elution will be very fast, but you will not get very accurate result if it is very low value. Factor is below 1, that represents below 1. If it is below 1, then elution will be very fast. You will not get the defined peak for calculating retention time. That's why it is making the determination of retention time is very difficult if it is very low and the elution is very fast. And if it has if an analyte has high retention factor, that is greater than 20, then it means it takes very long time for elution. What is ideal retention time? 2 to 8 minutes. So in that ideal retention time, we need to elute out completely your sample from the column. That means complete 100% elution should be achieved within the prescribed time. So that is depending on your retention factor of an analyte. If it is very less, that is less than 1, then you may not get the peak only within the prescribed time. It will be very fast. If it is more than 20, then it will take very long time. That is maybe more than 15 minutes for elution. That is also will not give ideal retention time or ideal separation or elution for the analyte. So what will be your ideal retention factor for an analyte? It should be between 1 and 5. Should be between 1 and 5. More than 1 and below 5. 5 or below 5. So not greater than 20 or less than 1. This is the ideal retention factor for an analyte to get ideal retention time. That is between 2 and 8 minutes. Okay. This is about capacity factor, which will affect column efficiency. Okay. So it is defined by retention time and migration time. It says about capacity factor, says about migration rate of an analyte on a column. If it is high, migration rate is very high, then elution will take more time. If it is very less, then elution will take less time, but you will not get defined peaks. So ideal retention factor K value will be 1 and 5, between 1 and 5. This is about capacity factor or retention factor. Clear? Next, we'll move on to selectivity factor. The fifth factor is selectivity factor. It is also most important when two analytes are eluted from the column. Okay, if two analytes simultaneously gets eluted from the column, then it should be of baseline separation we should get. Not like the first one, poor separation. Here you can see for two components, take A and B as two species are getting separated from the column, means if poor separation leads, that is alpha value, selectivity factor value will be of 1.1. So it shows not means no selective or specific compound is separated from the column. It is of mixture only shown. No ideally separated mixtures are shown here. It is coupled with or overlapped with other compound. So next is medium separation only occurs. No baseline separation is achieved, where alpha value is 1.3, which shows partial separation, but not that much selectivity. Even we can't take this as complete retention time calculation. Next, to get best selectivity and best separation, alpha value should be 2 or greater than 1. Mostly it should be always greater than 1, but if it is alpha 2, then it will give complete separation of or baseline with baseline separation of two molecules. This is the ideal separation, and this is defined by the factor alpha. Alpha is nothing but selectivity factor. It is denoted by the symbol alpha, which describes the separation of two species. What are the two species? A and B. Any drug molecule of A and B, two analytes, if it is separated simultaneously in the single column, then this factor is applicable. Here we can take K dash is what? Capacity factor of B and capacity factor of A. Ratio of capacity factor of second analyte. Second analyte will be eluted first. Then means it will take more time for elution. Means retention time will be high. So that is taken as first one, that is K dash B and divided by K dash A. This is for first analyte, which has less retention time, and this has more retention time. You consider this one for A and this one for B, second molecule. So the factor is taken for whichever is having high value as numerator, and denominator will be the retention time with low value. B and A. K dash represents capacity factor that we have discussed earlier. Migration rate of B and migration rate of A. And which will give you selectivity factor for two components. When calculating the selectivity factor, A elutes, this species A elutes very faster. That's why retention time is very less for first compound. It has been eluted from the column very soon, where second compound takes more time. We have taken in the x-axis time as the factor. That is called your qualitative parameter in column chromatography, right? What is qualitative parameter in column chromatography? That is retention time, which we have already discussed, where it reaches, the compound reaches 50% elution from the injection point, where A sample elutes very fast and B sample comparing with the B sample, and the selectivity factor always greater than 1. Since we are taking higher value for taking a ratio, then always it will be greater than 1, not in fractions. So it will be greater than 1, so that we will get baseline separation. Mostly at alpha value at 2, 1.5 and 2 will give you with baseline separation. But below 1.5 we'll be getting like a poor and partial separation only. Above 1.5 and 2, more than that, we'll get baseline separation of two components. Okay, this is the ideal separation with the prescribed retention time. So this is about selectivity factor, which also affects column efficiency. Okay, for two molecules. So what are all the parameters till now we have discussed under partition theory? From first, partition coefficient, that is distribution of analyte between two immiscible phases, stationary and mobile phase. Then retention time, that is time taken by the analyte from sample injection to reach detector, and or we can consider this as 50% elution. The sample has reached 50% elution from the column, or to reach peak maxima in the chromatogram is called retention time. Unit for retention time is minutes. And retention volume, what is retention volume? The volume of mobile phase taken for the sample to reach 50% elution is called retention volume, and it is depending on flow rate of the mobile phase. It is set with ml per minute. And ideal flow rate will be, ideal flow rate I didn't mention, it is will be 0.1 to 10 ml per minute. 0.1 to 10 ml per minute. We can use from 0.1 to 10 ml per minute as a flow rate for mobile phase, and it decides about retention time also, so that we can calculate how much retention volume of mobile phase is used for elution. Then migration time is mobile phase. How much time mobile phase is taking to pass through the column is called as migration time. And these two factors are used for calculating capacity factor or retention factor for an analyte. How long it stays in the column, that is explained with capacity factor or retention factor, and it should be between 1 and 5. Then selectivity factor is always should be greater than 1 for better separation with baseline. So observe this separation as ideal separation with baseline and has best selectivity, and retention time of first analyte will be always low and the second will be always high. So taking high parameter in the numerator and denominator, we will be calculating selectivity factor, that is represented with alpha. Alpha value should be 1.5 and more. Next we'll move on to another theory of column efficiency parameter, that is band broadening theories. These are very important under partition theories, you will be getting a 5 mark from directly from band broadening theories. Okay, this will also affect column efficiency parameters, or column efficiency affected by band broadening theories. So what are the two theories? Plate theory and rate theory. Band broadening theory is otherwise called as HETP, that is height equivalent to theoretical plates. Okay, so HETP for plate theory and HETP for rate theory, that we are going to discuss now. So band broadening theories will directly say about or depending on HETP. What is HETP? Height equivalent to theoretical plates. Height equivalent to theoretical plates. Plate height we have discussed under HPTLC and TLC, no, where you have discussed what is plate height, right? Even you got doubt. The plate height is nothing but HETP. What is HETP? Height equivalent to theoretical plate. It is most important term in the chromatographic analysis. Okay. So it is covered under band broadening theories, where this band broadening theories are coming under column efficiency parameters under partition theories. First we'll see what is plate theory. Plate represents stationary phase column, where plate is present, theoretical plates where it is located inside the column, where rate represents flow rate of mobile phase. So plate theory will be meant for stationary phase, and rate theory is meant for mobile phase. Okay, mobile phase flow rate and rate of elution, we can say. Here plate represents migration rate of, it will say about migration rate of your solute in stationary phase. So what is plate theory and rate theory, we'll discuss in brief. Plate theory is nothing but the plate represents the theoretical plates. Theoretical plates means hypothetical plates, what we are assuming to get according when we use uniform particles with uniform particle size, then we will be getting theoretical plates. Okay, so large number of separate layers that is formed due to uniform particles of adsorbent, then it will be giving large number of separate layers in the column. Those layers are considered as theoretical plates. Okay, you can imagine a column with several layers, and each layer is produced by your column material, that is adsorbent, and each layer is considered as theoretical plate. Okay, and separate equilibrations of the sample between stationary and mobile phase occurs in these plates. So each plate I told is meant for one analyte separation. So in if you have in the prescribed length of column, for example 10 centimeter column, if you have more than 100 number of theoretical plates in that, then we can separate that many number of samples. More than 100 samples we can separate in each plate that is present inside the column. And this plate height, if it is reduced, then we can separate more number of samples. How we can reduce the plate height inside the column? By reducing particle size of adsorbent. What factor is depending on plate height? Particle size of the adsorbent. When it is reduced, then plate height also will be reduced. Then number of layers in 10 centimeter prescribed length of column will be increased. So this is represented with HETP equals to L by N. L represents length of column, that is 10 centimeter column or 25 centimeter column, whatever length of column we are using, that is represented with L. And N represents number of theoretical plates. With that prescribed length of column, how many number of theoretical plates are present? How we can calculate number of theoretical plates? We don't know. It is a hypothetical plate, how much it will be. And we can, by using this formula, we can calculate how many number of theoretical plates being used for separation. You take 5.55 retention time square divided by width in the peak width. You can observe here is the retention time square. If you take this molecule to calculate a number of theoretical plates, take retention time, square of retention time, then peak width at half maxima. That is the half of the peak, half width at 50% or half maxima when it is reached. If you take the width of the peak, then it is that value can be used for calculating number of theoretical plates. So here W half, that is a half width, or we can say half maxima, width of half maxima. of the peak. Okay, the square of half width is taken for calculating number of theoretical plates. The factors considered here is 5.55, then square of retention time and square of half width in the peak. Okay, by using which we can calculate n, and that is substituted here to calculate HETP, height equivalent to theoretical plates. When height equivalent to theoretical plates are increased, that is height is increased means number of theoretical plates will be reduced. When height is that is inversely proportional. This is inversely proportional to the height of theoretical plate numbers. Then length will be directly proportional to height of the theoretical plate. When height is increased, length is also increased. When height is decreased, height equivalent to theoretical plates are decreased, the number of theoretical plates will be increased. Okay. And this factor is depending on particle size of the adsorbent. Plate theory is depending on particle size of the adsorbent. Okay. Clear how it is calculated? L by N. L represents length of column. N represents number of theoretical plates. The height of those theoretical plates only covering plate theory. And this height represents the separation of your sample between stationary and mobile phase. How many number of samples can be separated in this layers is depending on the height. Okay. Next, we'll move on to rate theory under partition theories, column efficiency parameters. It is also most significant and important theory under column chromatography, Van Dinter equation. It is defined by Van Dinter, the scientist Van Dinter. So, it is called Van Dinter equation. The HETP for rate theory. And it will tell about mobile phase flow, diffusion. Here you can see diffusion, different diffusions have been explained with the Van Dinter equation. So it says about rate theory. Rate represents migration rate of your analyte between two phases, stationary and mobile phase. How it is migrated, in what way, that is explained with this theory. So what is rate theory for HETP? That is Van Dinter equation. It is explained with Van Dinter equation. Van Dinter equation also, H represents here HETP. H represents height. Height equivalent to theoretical plate. That is equal to A plus B by U plus CU or U into CM plus CS. What is A? It is diffusion. It is or multipath diffusion. Yeah. Then B represents longitudinal diffusion, longitudinal or horizontal diffusion. Then CM represents resistance to mass transfer in the mobile phase. M represents mobile phase. C represents resistance to mass transfer. Mass here indicating analyte transfer, resistance to analyte transfer in the mobile phase. Then CS is resistance to mass transfer in the stationary phase. These are all the different factors we are going to discuss. In the coming slides, we will be seeing what are different diffusions and different parameters will be explained individually. What is eddy diffusion, what is longitudinal, and what is resistance to mass transfer in the mobile phase and in the stationary phase. And here U is velocity. Okay. Linear velocity. You can here in the graph you can observe linear velocity U in centimeter per second, and it is explained with this curve. Height equivalent to theoretical plates are taken in the y-axis, and the linear velocity of flow mobile phase is taken in the x-axis, and C term that is C term represents what? Resistance to mass transfer. And here it is explained here as kinetics of the analyte between mobile and stationary phase. Kinetics of the analyte that is in mobile phase and stationary phase, that is linear. Okay, C term. A term represents eddy's diffusion is depending on particle size and how well a bed was packed. That is column, how it is packing. It is depending on packing of column and particle size of the adsorbent. And that is depending on A term. That is eddy's diffusion. Then B term is axial diffusion or longitudinal, horizontal diffusion. Okay, actually your sample must pass through the column vertically, but instead of diffusing vertically, longitudinal diffusion occurs, and that is explained with axial diffusion. Since we cannot define the diffusion inside the column once your sample is passed, we cannot expect exact diffusion, vertical diffusion. So these are all the factors will affect column efficiency, so that only here are discussed. Okay. And next about lowest HETP, that is equal to optimum plate count. So HETP is indirectly proportional to the plate heights. Okay, plates, number of plates that we have seen in the previous slide itself. A number of plates are indirectly proportional. That is mentioned here. Okay, HETP is indirectly proportional to number of plates. So these are all the different terms, A term, B term and C term as described under Van Deventer equation. What is A? It is diffusion, and it is going to depend on particle size and packing, column packing. It is diffusion is depending on particle size of adsorbent or column material. Particle size and how well a column is packed. It is depending on column packing and particle size. Where C term is depending on kinetics of the analyte between stationary and mobile phase. B term is for axial or longitudinal diffusion. Okay, what is U? U is linear velocity. Unit is centimeter per second. Now let's move on to brief discussion about red theory. First one is eddies are multipath diffusion. Eddies are multipath diffusion, that is A term. It is described by 2 lambda dp. 2 lambda dp. Lambda is correction factor for the irregularity of the column packing. So I told it is related to the column packing and particle size. So that this lambda factor is related to column packing, and dp represents the diameter of the average particle diameter. D represents diameter, P represents particle diameter. So it is representing particle size, and lambda representing column packing. So what is exactly lambda is? Correction factor for the irregularity of the column packing. Correction factor for the irregularity in the column packing, that is set by lambda. And what is dp? Average particle diameter. Okay. So by using this formula, we can calculate multipath or eddies diffusion. So what is A? 2 lambda into dp. What is lambda? Correction factor for the irregularity in column packing, and dp is average particle diameter of the your stationary phase. Now let's see about longitudinal diffusion. This is depending on, that is the axial diffusion. Instead of vertical way of diffusion, axial or longitudinal diffusion occurs, and P is calculated by 2 gamma dm. 2 gamma into dm. What is gamma? Labyrinth factor for the pore channels, that is depending on the pores present inside the column for diffusion, that is explained with gamma. Dm is diffusion coefficient of the analyte in mobile phase. M represents mobile phase, D represents diffusion coefficient. Diffusion coefficient of analyte in the mobile phase, how much it is diffused in the mobile phase, your analyte. So these two factors will calculate longitudinal diffusion. Next about resistance to mass transfer, that is C term. CS represents resistance to mass transfer in the stationary phase, and DF here it is calculated with DF square divided by here it is square divided by DS. DF is representing bandwidth, stationary phase bandwidth, and DS is diffusion coefficient of analyte in stationary phase. Already we have seen what is DM. It is DS. DS is diffusion coefficient of analyte in stationary phase. And CS is concentration of analyte in stationary phase, or we can say mass transfer, resistance to mass transfer of analyte in stationary phase. S represents stationary phase, C is mass transfer, resistance to mass transfer. DF is representing thickness, stationary phase bandwidth or stationary phase thickness, we can say here. Here 2 represents square of DF, okay, the square of DF, and DS is diffusion coefficient of analyte in stationary phase. And this for packed columns, CM. Here CS and CM are there, right? Here you can see mass transfer is for sum of mass resistance to mass transfer in mobile phase and stationary phase. Here CM for packed columns like HPLC, GC, for those columns, it is calculated by dP square divided by dm. dP, what is dP? Particle diameter. Packed column, it is depending on particle diameter. Here it is mentioned dP is particle diameter, as we have discussed under A. That is AD's diffusion. dP is particle diameter. And for open columns, it is defined by DC square divided by DM. DC is column diameter. For open column, it is depending on column diameter. For packed column, it is depending on particle diameter. Okay, it is square by DM. Here it is DF square by DS. For CS, it is depending on stationary phase bandwidth. For stationary phase, it is depending on stationary phase bandwidth. Where mobile phase, it is depending on diameter of the column or particle diameter. Okay, this is about rate theory for resistance to mass transfer for stationary phase and mobile phase for an analyte. Okay, so these are all the three factors under HETP for Van Dimter means HETP in for columns according to Van Dimter equation. So what is HETP? A plus B by U plus U into C M plus CS. Sum of Cm plus Cs. Okay, or we can call this as Cu also. C into U. C can be written as mobile phase and stationary phase. Sum of mobile phase concentration and stationary phase concentration. Clear now about Van Dimter equation. And C term is depending on kinetics of the analyte between mobile and stationary phase, where A term is depending on particle size and column packing, and D term is depending on axial diffusion. So diffusion is depending on the mobile phase, diffusion coefficient of analyte in mobile phase here. And the gamma represents labyrinth factor. Here it is lambda, here it is gamma. Factors are depending on different parameters. So this is about rate theory and plate theory under band broadening theories under column efficiency parameters. Next, the last parameter is resolution. It is most important parameter, resolution. Okay, and resolution value also should be 1.5 to get baseline separation. It is also like a selectivity factor, but it is not related to selectivity factor or not same as selectivity factor, where selectivity factor, that is alpha, here alpha describes the separation of band centers, right, where exactly it is separated, but it does not take into account peak widths. Peak widths are not peak widths, that is width of the peak from half maxima. At half maxima, what is the width? That width is not defined by selectivity factor. We'll check once again whether selectivity factor is explained with peak width. It is not related to peak width. It is related to retention time and migration time. K. What is K factor? That is capacity factor. It is related to capacity factor. Here also it is depending on the time, not width. Everything is said in time, elution time, migration time. But your resolution is depending on width of the bandwidth of the chromatogram or your analyte. Okay, so that is the difference. Even it is calculating retention time along with width of the two analytes, peak width of the two analytes. W represents peak width, TR represents retention time. And resolution also applicable for two species, whether it is with a high resolution, whether it is separated or not. It is also saying baseline separation of two molecules, whether it is achieved better or not. When it is achieved better, when resolution value is 1.5, and it is denoted by the symbol R. Resolution represents R resolution. It is of 2 times retention time of B, analyte B, and retention time of analyte A. 2 times 2. It is multiplied 2 times B and A. Difference between retention time of B and A divided by width of first analyte and width of second analyte, A and B. It is sum of the peak widths of A and B. Will give you the baseline resolution or resolution of any analyte, and it should be 1.5 1.5. Optimum resolution is 1.5. What is the optimum selectivity factor? That is 1 and 5. Between 1 and 5, right? 1 and 5, not, sorry, that is capacity factor. Selectivity factor is greater than 1. It should be greater than 1. That too, it should be 2 for getting baseline separation. Where 1.1, 1.3 are showing poor and partial separation. Likewise, resolution also should be 1.5 for optimum peak resolution, okay, or optimum peak separation. Resolution and peak separation. This diagram represents. So here overlapping of your peak is mutual, 0.15% mutual, here 2.3% mutual, but it is not touching the baseline only. So baseline separation is must for getting ideal peak separation. So ideal peak separation of two molecules are explained by two factors under the partition theories. First one is, it's all you must understand, then only it is easy when you are getting into different chromatography, column chromatographic techniques. So how resolution is calculated? It is 2 times of difference between difference in retention time between second analyte and first analyte. Second analyte retention time will be high than first analyte, right? That's why we have taken retention time of second analyte in the beginning for calculating the difference. Then divided by the sum of peak widths of first and second analyte. Will give you the resolution, and it should be optimum value should be 1.5 to attain with the baseline separation, and it is not depending on, or it is not another factor for selectivity factor. It is also different parameter, since it is explaining about peak widths, where separation selectivity factor only says about migration time. So these are all the partition theories. With this, I'm completing the basics of column chromatography. In the next class, we will be seeing about column adsorption chromatography. We will be getting into actual column chromatographic techniques with the different chromatographic parameters we will be discussing. So with this, history of column chromatography, principles of column chromatography, and theories of column chromatography we have discussed. History, principles, and theories we have discussed. And the principle, adsorption, partition, ion exchange, size exclusion, gel filtration, this all we have seen. And in that, different chromatographies we are going to discuss. And theories, adsorption and partition theories we have discussed. Adsorption, linear, non-linear, Hendry's, Freundlich, bed theory we have discussed. And under partition coefficient, retention time, retention volume, migration time, capacity factor, selectivity factor, band broadening theories, plate theory, rate theory, is all we have discussed along with the resolution factor. Thank you all. If any doubt, you can discuss now. For all, advance a happy Pongal. So after Pongal, we'll meet with the next column chromatographic technique.
Thank you, ma'am.
Same to you, ma'am.
Thank you. Is there any doubt?
Thank you,
Clear about HTTP, no? HTTP is most important part in the chromatography. Monisha, clear? Last time you had doubt, no? HTTP. Can you relate this HTTP with the plate height there?
It's not clear, ma'am.
Okay, pa. Okay. Thank you. Thank you all. We'll meet after Pongal holiday.
Ma'am, am I audible, ma'am?
Yeah, Jackson.
Ma'am, I have replied for your question, ma'am.
Okay.
But you are not audible, it seems, ma'am.
Yeah, you didn't on your mic only. Then how I will get your voice? Now it is clear. Now
Ma'am, now
clear.
I have, in between, I have left the class and I have joined again, ma'am.
Okay, that's okay. Now you can say what we have discussed also. If you want, you can discuss now. If you have any doubt, you can clarify, or else you can say what are the topics we have covered. If you have attended the class completely.
I have attended, ma'am, today.
Okay. Attended, no? Clear, no?
Yes.
Respond pannu. Whenever I ask question, you have to respond. You have to give
Ma'am, I have replied, ma'am, but you are not audible, ma'am. So I have text you in chat box, ma'am.
Okay. I didn't see that. I will be seeing. I have recorded, no? So I'll see your chat messages. I'll see later. Okay.
Okay. Okay, ma'am.
No
Thank
problem.
you.
Thanks for your response. Many people are
Okay.
not responding only. You have responded. That's good. We are learning, then better. Okay. Okay, but
Okay.
we'll stop the class now. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.